Okay, this is going to be one of the important chapters in this course. You will understand why probably towards the end of this lecture. Now, in this lecture, we will talk about DACs and ADCs, which are digital to analog converters and analog to digital converters and their programming in AVR. Now, we'll see what is analog to digital conversion and the converters that we use, some examples, discrete components and analog to digital converters, some subsystems and discrete ADC components, analog comparator, and so on. Now, if we start with a general analog to digital conversion, my first question is going to be, why do we need analog to digital conversion? Why is it so important for us that uh, we have to use it, and how we use it, we are going to see in this chapter. Now, when we think about the world, the real world actually, the parameters are all analog. Think about the temperature, think about the speed, the pressure, the wind, the sun. These are all having analog features, voltage, current, and so on. And let's say we have got the analog world on one side, okay? And if we are using these digital computers, microcontrollers, microprocessors, we need somehow, let's say digital computers, we need a way to interact. So we need some kind of protocol, something in between those two important elements, because the devices are digital, the world around us is analog. We have to somehow interface directly with the real world. And why do we need to do that? We need to measure the temperature, we need to measure the speed, the pressure, the wind, the voltage, the current. Okay, we have to measure these in order to process these data, or in order to control a process. We need to do that somehow. And that's why microprocessors, microcontrollers, or digital computers in general, they integrate these analog to digital conversion circuits or converters or techniques in order to deal with these analog measurements or analog inputs. So that's why it's so important to interact with the world, and as we are using digital devices, we need some kind of bridge, some kind of communication with the outside of the device. So what I have already told you about, the real world parameters are analog in nature. That's why we need analog to digital conversion. So the figure over here demonstrates how these are happening in a complete system. Now, sensors, which we are going to talk about in a minute, it's actually reading the values from the nature. So they are taking the analog values, converting them to some electrical values. It can be a wind, it can be a pressure or temperature, whatever they are. Now we need these devices. So why are we using MAX over here? That's something that in order to have analog to digital converters, now this is not a small device. We need many of these. If you have, let's say, 4 or 5 sensors, then you need 4 or 5 analog to digital converters, which is going to be an expensive, costly, area-wise, power consumption-wise. So that's why we use MAXes, so we can direct number of sensors into these maxes, and we can actually choose to read which sensor or which channel we want to read. Okay, so we can read one channel at a time rather than having separate unit of these signal conditioning and then A to D conversion. That's why we use maxes, and the same applies over here as well when you want to use actuators to convert any of these electrical signals into some mechanical, for example. Okay, so these triangles, as you can see, they are the signals conditioning circuits. So why do we need these signal conditioning circuits, which they are operational amplifiers or differential amplifiers or isolation amplifiers? Now, sometimes these, or the most of the time, let's say, the sensor values that we are reading are small values. And in order to have a good gain and good reflection of the voltage that we are measuring, we need some signal conditioning circuits in order to have proper, not distorted or not lost signal to process it in analog to digital conversion, so that microprocessor can use that process signal to do some operations. That's why we need signal conditioning. And the same applies for the digital to analog as well. So when we are activating these actuators, we need a proper signal over there. That's why we need signal conditioning. We'll talk about them in details later on. And of course, analog to digital converter and digital to analog converter, they're important as we are going to convert the analog signal into digital, which I will show you the techniques, and digital signals to the analog. Then when we have the digital signals and bits, they can be easily read by the microcontroller and process the data and do some other operations. Or even we can get this digital data converted to analog and activate some of these mechanical devices like actuators. Okay, so let's talk about some terms that are used in analog to digital or digital to analog conversion. Transducers, which we call them the general device names as for the sensors and the actuators, because they can convert a process variable like temperature, speed, or something else into a electrical signal, okay, or vice versa. So it's like a converter between some electrical to maybe a mechanical or something else. And sensor is actually an input transducer, we call it. So we generally call it sensors in order to do some measurements. So they convert the process variable into an electrical signal as an input device. And actuators are the opposite of that. It converts an electrical signal to a process parameter. Okay, so these are some of the terms that we need to know and understand before we dive into the analog to digital, digital to analog conversions. And we can give some example to these sensors like position sensors. Probably you're all familiar with these. You can find them in your mobile phones, you can find them in your smartwatches or any type of system that we are having digital electronics in there, you can find these sensors. So position sensor, they generally use potentiometers. So based on the angular position of the shaft, okay? So there's a constant current, DC current input over there, or force strain gauge. So it's like a resistance variable with stretching. So it's just generates a vibration or something like that. And temperature, we generally use, we can have a thermocouple, which converts the change in the temperature into a current again, or maybe a voltage. And thermistor is an example of that devices, which is resistance varies with the temperature. Light intensity, photoconductive cell, so phototransistors, for example. Again, DC current in proportion to the light intensity. And the current transformer or SenseFET, current sensing power MOSFETs. So they are all type of sensors that we generally use in digital electronics. Okay, so before we move on, we have to know and we have to understand some of these digital to analog, analog to digital parameters and specifications actually. And VREF is one of those. Now, VREF is actually the reference voltage. It's an input voltage used for reference. And the voltage connected is along with the resolution of the ADC chip. It dictates the resolution size of the ADC chip, okay, which actually dictating the step size. So, for example, when we talk about 8-bit ADC, okay, the step sizes, which I'm going to talk about in a minute, is VREF over 2 to the power 8, which is going to give us VREF over 256. Now, if the analog input range needs to be 0 to 4 volts, for example, then VREF is connected to 4 volts, okay? And we can say that 4 over 256 will have 15.62 millivolts. Now, VREF is important, and we'll use VREF a lot in order to calculate the resolution, the step size, and so on. Now, another important thing is the offset. Now, offset, when we think about the offset, it's the minimum analog value represented by the digital code. So it's actually the VREF minus, okay? And whenever for example, digital to analog have got lowest voltage trying to detect, the offset associated with that may be the lowest voltage that is coming from the supply voltage of the system. So, for example, with the DACs, it's common to find that minus VE is connected and also the plus VCC is connected. So, in AVR that we are going to use, VREF minus is actually 0. Okay, so this is something that we use for AVR. That's the specs for the AVR. You can find that in the data sheet as well. Okay, so what is span? Now, span or a range, or maybe we can call it a full scale voltage. It's actually the difference. So it's actually the min to max analog difference. So VREF and the span is generally given as VREF plus minus VREF minus. And when you think about the AVR span, as VREF minus is 0, you can just have VREF plus minus 0, which is equals to VREF plus. That's what we are going to use in AVR. Okay, another important metric or the parameter is the resolution. Now, what is resolution? Now, whenever an input is changed, what is the maximum voltage or current that changes at the output? Or what is the required change in input in analog setting so that there's a 1 bit of change at the output? So this is what we need to answer as a resolution. So resolution is the smallest analog change that can be distinguished by the analog to digital converter. So the ADCs has an n-bit resolution where n can be 8, 10, 12, 16, depending on the component that you're using, or maybe the microcontroller that has specific ADCs in there, they can have a different resolutions. So higher the resolutions, ADC provides smaller step sizes, where step size is the smallest change that can be discerned by an ADC, as we already said. Okay, so when we consider these, resolution and other things, we can say that resolution, let's draw this table. Resolution versus step size for ADC. Let's say the reference voltage is 5 volts. Now, n bits is actually defining our number of bits. Then we have got number of steps, and of course step size, which is in millivolts. Okay, so for example, if we have an 8-bit, then the number of steps is to the power h, which is 256. So the step size is 5 over 256, which is 19.53. Okay, maybe we had to tidy it up that. So let's say we have got 10 bits of resolution. That's going to give us 2 to the power 10, 124. And that's going to be 5 over 124, which is going to be 4.88 millivolts. Or 12-bit resolution, it's going to be 2 to the power 12, which is 496. And that's going to be 5 over 496, which will give us 1.2 millivolts. Or 16-bit resolution, then 2 to the power 16, which is going to be 65,536, and again VREF minus 65,536 will be 0.076 millivolts. Okay, now you can see how the resolution and the number of steps and the step size is calculated by this table. Now, although the resolution of these ADC chips are decided at the time of the design, and we cannot change it, we can actually control the step size with the help of the reference voltage. So the resolution is actually showing the accuracy of the conversion between analog and digital signals. And the general formula for that, let's say the resolution, which you need to know this formula, or step size is equal to span over 2 to the power n, where n is the number of bits. So in this case, AVR resolution is equals to span is VREF, as VREF minus is 0. So VREF to the power n that we can consider. And we can also easily find out the percent resolution, which gives us the percentage of it. Now the percent resolution is step size divided by span multiplied by the 100. Okay, so we can easily get the step size that we have calculated over a span, over a range. That will be multiplied by 100 to get the percentage. Or you can just say 100 divided by 2 to the power n percent. That's also possible. So these are some of the formulas that we need to consider. Okay, so another parameter or another important metric is the weight. Now, weight of the least significant bit is equal to the step size or the resolution. And in general, when we talk about the weight, for example, let's consider digital to analog or analog to digital is actually an 8-bit. Okay, so ADC or DAC is an 8-bit. Okay, so if DAC or ADC is listening these bits, let's say bit 7, bit 6, bit 5, it goes down to bit 0. Now, each of these bits have a different weight in terms of the conversion to the analog parameter, and it set the resolution or the accuracy by least significant bit change. So whatever that analog change corresponds to least significant change is the resolution. But then, for example, B1. So we have got B1 as well. Now, what will happen here? When we are changing the weight associated with this B1, it's not small as B0 when you consider it. The weight is higher. Now, when we are changing B1, we are actually changing large voltage or maybe a larger analog parameter. But it has certain weight associated with it that is larger than B0. And the same applies for the others. So for example, B7, which is the most significant bit, has got larger weight. And when we change B7 input of the DAC or output of ADC, that means we actually covering half of the range of the full span. So it's actually the half of the weight is coming from the most significant bit, as it has got the highest weight. Okay, so when we start talking about, when we do an examples, you will understand better how these things are going to be put up together. So conversion time, for example, it's another important thing. Now, what is conversion time? It's actually defined as the time it takes analog to digital to convert the analog input to a digital, for example. So that's actually the duration. Now, it actually tells us how often we can sample. And there's one important thing in the conversion time is the settling time. Because when you get this value and it takes some time to settle down because you might have some distortions, you might have some noise, okay? And normally these ADCs or DACs, they are giving just this settling time as a parameter like 100 nanoseconds, for example, so then you can have a reliable value that you can use to process it after conversion, okay? So we had to take this into account. And it is generally dictated by the clock source connected to the ADC, in addition to the method used for data conversion and technology used in the fabrication of the ADC chip. So these are important things when we consider the DACs and ADCs as they are having the major parameters. Parallel and serial, so as I already mentioned over here, we can have channels that we can read one by one. And that's why we use multiplexers over here so that we can have a parallel sensors connected to the ADC. Or you might have a serial connection where you can have only one sensor connected to the ADC, which you need to shift in. You can use the shift registers to shift in the values. And input channels, we can have, again, in the multiple input channels that we can read them by using the multiplexers. So the calculation or the formulas that I have already mentioned over here, that you can also find in the lecture notes. For resolution determines the accuracy of the conversion. So step size, span over 2n. And for AVR, this is VREF over 2n to the power n. And the percent resolution is calculated as follow. Now, another important thing is the ADC digital output. So digital output, for example, of 8-bit ADC, again, it's going to be from D0 to D7. Or 10-bit, this is going to be D0 to D9. Okay, now how do we calculate this D out? It's actually the voltage in divided by the step size. Now, what is voltage in? Voltage in is actually the analog input. Okay, and if there's an offset, then that's going to be voltage in minus the offset divided by the step size. Okay, so that's how we can find out the digital output. So based on these parameters, let's do a couple of examples in order to understand how these parameters are actually affecting the calculations. Okay, so the analog range is given between minus 5 volts to 5 volts, plus 5 volts. Digital range is 8 bits, so 2 to the power 8 minus 1. So 8-bit resolution is given over here. What are the offset, span, step size, and percent resolution weights? So when we consider the first one, offset, we already said that it's the minimum value that we can have, which is minus 5 volts. Then span is the range, which is 5 volts minus 5 volts, which is going to give us 10 volts as a range or the span. Now, the step size. So, step size is, we know the span divided by 2 to the power n. In this case, span is 10 volts divided by 2 to the power, so 8-bit resolution, 2 to the power 8, which is going to be 10 volts divided by 256. And this is actually going to give us 39.1 millivolt as the step size or the resolution. So then the percent resolution is going to be 100% divided by 256. If you want, you can calculate like that, or you can use the other formula, 0.391%. So that will be our percent resolution. And the weights. Now, what are the weights? How do we calculate the weights? So let's say digital bit and its weight. So starting from, we have got 8-bit over here. So starting from 0, then weight of that is 10 volts divided by 2 to the power 8, which is going to be 0.039 volts. So LSB is deciding it, again, as you can see. Now, the digital bit 1, it's going to be 10 to the power 7, which is going to be the double, so 0.078 volts. Then digital bit 2, it's going to be 10 over 2 to the power 6. Again, 0.157 volts. Bit 3, then 10 over to the power 5, which is 0.313 volts. Bit 4, 10 over to the power 4, then it's going to be 0.625 volts. Bit 5, it's 10 over to the power 3, which is going to be 1.25 volts. And bit 6, it's going to be 10 over to the power 2, which is going to be 2.5 volts. And bit 7 is 10 over to the power 1, which is going to be 5 volts. Okay, so these are the weights that we can find based on the digital bits. And part B, it says what will be the digital output for the following inputs: -5, -3 volts, 0 volts, and so on. Now, digital output, we know the formula for it, which is D out is equals the analog voltage minus the offset, okay, divided by the step size. So when we think about -5 volts, this is going to be 0. -3 volts, this is going to be 51 or X33. You can do the calculations. 0 volts, then it's going to be 128, which is 80. And we can have, the last one was 4.961, which is 256, and that will be FF. Okay, so 5 minus 0.031, 391, and so on. It goes like that, which we can get these values. So we are actually picking the closest integer to make it accurate, because this is 255.000016. Well, so we get it as 256. Okay, so you can find the answers over here as well. Example 2, 8-bit ADC have VREF 256 volts. Calculate the D0 to D7 output if the analog input is 1.7 volts and 2.1 volts. Okay. Now, we know the voltages again. We need to calculate the outputs. So the VREF is given as 256, and we can assume the offset to be 0. It's not given, so it's implied that it is. And it's an 8-bit ADC. So offset is equals 0 volts. And step size, we can have 2.56 VREF divided by 256 to the power 8. That will give us 10 millivolt step size. So in A, what we are looking at is D out, which is going to be V in over step size. So this is going to be V in is 1.7 as it is given in the question, divided by 10 millivolts, which is equivalent to 170. So what is 170 in binary when you consider 8-bit? 170, if we go back to the logic, bit 7, 6, 5, 4, 3, 2, 1, 0. 128 plus 64 is going to be too much. 32, 128, then it's going to be 32. So 128, 32, it's going to be 130 and 150. So then 160, and then we have got, if we have 2 to the power 4, 16 is going to be too much. We need 10, so 8 plus 2, and we'll get 170 in binary. Okay, and we repeat the same thing for part B. D out equals V in minus step size. So V in is 2.1 volts divided by 10 millivolts, which is equals to 210. So 210, once again, 7, 6, 5, 4, 3, 2, 1, 0, 128, 64. So that will be 32 is going to be 0. Then 16, that's going to give us 64, 16, it's going to be 80, and then we have got 128, 28, and we have got 2 more, and the rest will be zeros. So that will be 210 in binary. So this is how we can actually calculate, based on the given analog input, we can actually find the digital output, and so on and so forth. And we can use the parameters, and we can find the resolution, percent resolution, weights, and so on. So if we understand the basics of analog to digital conversion, digital to analog conversion, then we can easily understand how we can use these components or the resources in the microcontroller in order to do some embedded applications, read sensor values, and process those values and do some actions related to those. And this is what we are going to see next.